Hello friends, today I'm over here to discuss Stack Overflow in ARM exploitation. The goal of this small video is sort of to show you an exploit program that I have written which works on iPad version 5.2. My iPad has already been jailbroken, so it's easier for me to push any programs on the device. That makes it easier to sort of experiment with respect to stack overflows, heap overflows, and other exploitation-based techniques. So in this video, the goal is basically to create a simple program that has a regular stack overflow and then exploit that, giving you few basic identifications for ARM assembly and a few simple pointers for ARM assembly. So let's begin. If you can take a look right now, what you're viewing is basically a simple C program that has been written. In this case, we can look at the three different functions. The first function is called donut. Basically, all it does is it prints a donut and then does a string copy of a specific command that I have provided to it, and then calls a system on it and exits. The next one is basically the vuln function, or the vulnerable function is what I would call it as. If you observe over here, there's basically a character buffer of 12 bytes, and it's being passed on in gets. This is where basically the stack overflow will take place, where when a user is providing more than 12 bytes, it would result into a simple stack overflow. The next is a regular int main function, which ends up calling the vulnerable function with the argument v1. And as I mentioned earlier, we can take a look at it, how it flows through the program and how we are able to exploit it. So let's go back to the shell. In this case, I'm using a PuTTY connection to my iPad. In this case, let's take a look at this program. So what I'm going to do is do a gdb exploit. At this point of time, let's look at the vuln function. So basically, the way ARM assembly works is that it's 4-byte aligned. So you will always see that all the addresses are 4-byte aligned. And if you're familiar with sort of x86 programming, you might have kind of understood the fact that x86 is extremely dense. It does not require that every assembly line should start at a specific d word of which is divisible by 2. So in this case, in ARM, however, you do have that requirement where basically every assembly line should begin at an address that's divisible by 4 or 2. So this is sort of a quick reminder with respect to ARM assemblies. As you can see, ARM does not technically use stack for passing on arguments. The arguments are actually passed through registers. The register R0, R1, and R2 are used primarily for arguments. The registers R4 to R11 or R10 basically are used as scratch registers. The R13, which is supposed to be a stack pointer, and R15 is the program counter, which you know as the instruction pointer in x86. So if you look at it, basically there's also a link register. The link register, or LR in this case, basically contains the return address. So whenever a program calls another function, it basically pushes the return address, which is the next instruction, into the linked register. However, as a part of sort of the ARM prologue, you can see that that register is actually pushed onto the stack, and that's basically where you can override this return pointer. And as you can look at instruction 2F24, finally the program counter is popped up with the link register's value, and that allows basically in this case to do a stack overflow. So what I'm going to do is I'm going to put a breakpoint just before the pop, so we can observe how the stack looks. Alright, let's begin the program. I'm going to provide it BBBBCCC D, which is basically, these are all the 12 bytes have been utilized by CCC and DDD. What I'm planning to do is provide EEE and HHH. This has been observed after I have done observations on the stack. It seems that there is a register R7 being pushed along with the link register. So the value E will be actually, put back into R7, and your link register should have the HHH value, which would be 0x58, 58, 58, and 58. Alright, let's begin. There's a breakpoint at as we had anticipated it. Let's look at the stack pointer. As said, if you look at the specific stack pointer, there is 0454545, which is your all E's, followed by 484848. If you do an SI, that is step instruction 1, you can see that it does say kernel invalid address, and the address has been overwritten with 48484848, which is your HHHH. Pardon me, I had said 0x58 before, but it's actually 0x48, which is the hexadecimal value in the ASCII table set for H. So now that we can see that we are able to overflow the stack pointer, it seems like, what do we do with this? So let's see the normal flow of this program. I'm going to debug out of the GDB. So what I plan to do is to exploit, pass it a regular value, and what it says is this is the normal flow. Observe that in the beginning that I had shown you this function, there was a function called donuts. What if we can call actually donuts and actually execute these commands? It doesn't seem like there's any call to this function, but if we are able to use the Stack Overflow correctly, we should be able to call donuts using our Stack Overflow example, and thus execute a function that does not exist technically or is not being called from the main program. So let's do that. Exploit. Let's break at the same pointer, which is 0x2f24. Let's do a test as donuts. Yeah. Basically, this function is loaded at 2e9c, and if that is correct, this value should remain constant. Observe that it does have 2 zeros before 2e9c, which means that we can only basically call this function and not execute any shellcode. Also, a quick reminder, on iPad version after iOS 4.3, they had enabled ASLR as well as the NX bit, which does not allow basically an attacker to execute the shellcode on the stack directly, and also the ASLR sort of bypasses or prevents an attacker from using return to libc functions directly from calling those functions and actually executing payload that way. However, I'll show you two methods. One will be a return to libc in the next video, which would help us to sort of bypass and execute our functions or shell functions. Obviously, at that point of time, we will be using hardcode addresses. One thing about iPad is that these library addresses will change every time you reboot. So basically, it's only useful within a single instance of your iPad being started and not rebooted, before you can use that address. So let's look at this regular exploitation first and then move on to the next one. So let's provide, so now that we know what the address is, observe that I had to use gets function as opposed to a string copy or mem copy as the function. It seems like the iOS SDK does use on the compiler actually sort of inserts the stack check guard functions. These functions are created specifically for string copy, mem copy, string cat, string ncat kind of functions, which are susceptible to Stack Overflow, where basically the compiler inserts a check guard function that ensures that if you try to overflow those that specific buffer with those functions, you will actually end up having a kernel panic. Rather than saying kernel panic, an application panic, and that would not allow you to actually execute a Stack Overflow. The gets function, however, is not sort of supported by iOS SDK. That allows me to sort of use this program to show you this demonstration. So as we had observed, what I'm going to do is I'm going to pick up quickly the values, and this is sort of the printf function that allows us to pass the values to the exploit. Observe that I am passing the same way, except at the last part I'm actually passing rather than HHH the address that we had observed just now, and let's see if that works for us. and there it is. It says donuts and it prints ls minus ltr and the id command. So that's sort of a quick overview of simple stack overflow. If you'd like to look this in GDB, you can basically use a less than sign and pass the printf values. However, I intend to do it without GDB just to show you quickly that this can be done without GDB as well. So that's pretty much it for assembly-based Stack Overflow. The next video will focus on the return to libc functionalities. Thank you.